here to the Aggies Invent, the final presentations to Aggies Invent that we have going on that's been sponsored by Los Alamos Labs. This is all on nuclear security. Those of you who have been here have been spending the entire weekend working on solving some really difficult problems, and we really have been amazed at the progress that you've made. I know we've pushed you hard throughout the entire weekend. However, you have really come up and done a great deal of work and a great job throughout this entire time. Just to remind those of you who are watching online and also for you watching here live, there's going to be 9 different presentations. The 9 different presentations are going to be 10 minutes long, and then the judges will have 5 minutes to answer questions. Participants, I'm going to have to ask you to use a wireless mic today. So we're going to use this mic so everybody online can hear, as well as we're going to be able to live stream this on YouTube, so you'll get a chance to take a look at it. I will recommend that you take a look at your YouTube. You'll hate yourself on YouTube. I promise you, you'll hate your presentation. I do all the time, but it's a great way to learn and to get forward. One of the most important skills that you're going to use and develop as you go through your career is being able to make effective presentations, and that's what this is all about. So, without further ado, my name is Rodney Boehm. I run the Engineering Entrepreneurship Program here. We've been your host for the entire weekend. The whole weekend's been sponsored by Los Alamos Labs. And now we're going to hear from the judges that we have who are going to be trying to determine which one of you will take home the first prize. Again, to remind you, the first prize is $1,000 to the team, the next prize is $750, and the third place is $500. However, more importantly, what we want you to do is to realize that if you're ready to continue to develop your product and you want to create a startup, Engineering Entrepreneurship is here ready to allow you, and we will help you throughout your entire career. We have an incubator right upstairs that's going to give you that opportunity to continue developing your product. So without further ado, I'm going to ask the judges to introduce themselves, and we're going to start on my right with Duncan, and they'll introduce themselves and give you a little bit of their background, and then we'll get forward with the competition.
Hi everyone, I'm Duncan McBride with Los Alamos National Lab, and my background is PhD in physics and about 25 years working at the laboratory on a wide variety of national security problems.
I'm Adam Wachter. I'm the deputy leader of Los Alamos National Lab's Engineering Institute. I've been for about 13 years, and my background is in mechanical and aerospace engineering.
Hi, I'm Ryan Sather. I'm a managing director at Accenture. We're a large global consulting firm. I'm excited to be here today. I look after part of our power generation business, which includes nuclear energy for commercial purposes. So I'm looking forward to your guys' presentations.
Obio Swarji. I'm also part of Accenture. This will be my 5th or 6th Aggies Invent, I think. My background, I graduated A&M, class of 2012. Whoop. Industrial engineering, undergrad, master's industrial engineering as well. I'm just happy to be here. I'm excited to see what you guys have today.
Howdy, I'm Diane Hurtado. I'm Associate Vice Chancellor for National Labs in our National Labs office, and my background is in aerospace and interdisciplinary engineering, and I got all 3 degrees from Texas A&M. So I'm really looking forward to seeing what y'all have done for the lab here.
All right, outstanding. All right, let me invite the first team to come up. It's 4.0 Cleaners. If y'all will come forward and get ready to give your presentation. I think we have it ready up on the screen, and we are looking forward. Again, timer in the back. We'll start the timer as you start your presentation. Clicker's right here. Please use the mic.
Thank you so much. 4.0 Cleaners, and today we are tackling the issue of contamination detection systems. My name is Zhanqi Wang. I'm a junior nuclear engineer.
My name is Esther Oyenegi. I'm a student. I am a senior MMET major.
My name is Diego Contreras. I am a sophomore in chemical engineering.
My name is Junseok Kim. I'm a senior student in nuclear engineering.
My name is John Paul Poso, and I'm a freshman in general engineering.
All right, imagine a scenario. You are currently working at a chemical plant, and something just went terribly awry. Something might have gotten out, you're pretty sure it's radiation. However, you're not sure. Instead of risking the lives of the people you work with, you decide to go another route. So what do? You look towards us because we have the innovation that you need. We have designed something called the atomic ant that is going to be able to fit within a 12 centimeter diameter pipe, operate wirelessly, operate within 50 meters of the operator or further, report the severity of the radiation, and be autonomous, meaning it could operate by itself.
Decided on the snake model. However, it was inefficient because it could only move laterally. Afterwards, we pursued the track model. It could not only move laterally, but could also rotate. After analyzing our failures and successes, we decided to pursue the ant model.
So for our model, we decided to use high torque motors. And so the purpose of this is so that whenever our model's inside of a pipe, whether there be rubble or debris or some kind of deformation, be strong enough to power through that. And so for our three-track system we have shown, the idea behind that is to have several points of contact throughout the pipe and be able to use it whether it's horizontal or vertical. And our three-track system, the tracks have attached to them, and that is inspired by the Ripsaw track suspension system. And here's an image of that. So the part that inspired us was the springs attached to the wheels and the tracks. So what that allows us to do is that if for some reason the terrain gets rough or the level of the flooring changes, the tracks will be able to adapt to that. And so we're applying that to the pipes. We don't know what kind of deformations may be in there or what kind of things we'll find. So we want our robot to be able to move in multiple directions and through any materials that may be in our way.
Our design consists of a camera, an LED, and a laser driving system to effectively determine the distance between the machine and the wall in the pipe. We use the GM counter to detect the radiation, and we use integrated Arduino for the Wi-Fi connectivity. The capsule is what we have in the back of the machine. Is where we keep all the electronic components, and it has a small vacuum that will be used to contain samples of the contamination we see. The estimated total battery time of the machine is 37 hours.
So, you might be asking yourselves, why are we different? Why not go for any other robot on the market? Why should you go for us? I believe this comes down to our size and flexibility. Our small size allows us to travel not just in 2 dimensions, but also in the 3rd dimension, going up pipes and down pipes in a steady and controlled decline. We can also detect radiation with our Geiger counter. Using this, we can readily see just how many counts a minute we are detecting, and once we found a peak, we can assume that that is where the contamination is. We can also be considered as hybrid, meaning that if the operator wanted to go home for the night and just set up the machine and let it go through the labyrinth of pipes and see what it finds, you can do that. You can definitely do that. You can also make it completely manual, meaning you'll look through the camera that is on the front of our machine, be able to not just look for radiation, but also look for cracks in the pipe or buildup in the pipe or many other applications. There's also something we are very proud of, which is our mapping. Our mapping is going to allow us to see what the speed is of the machine as well as what angle it's at. And thus, we can create an electronic map of the piping. That way, it can get itself out. It can also be able to tell the operator just what it looks like inside some pipes. Because let's be honest, you can't see inside the pipes. So, for future designs, a lot that we have not actually added to the CAD model. However, these are things of implementing. So, we have a rotation that comes out of the main body and allows it to rotate in the pipe and not to move in the third. This way, be able to grab a lot more contaminations. We can see a lot more things and be able to get through a lot more obstacles. AI driving, which means using an AI software, we can use the cameras themselves, and instead of the lasers, this way we can be able to get rid of some useless laser that's not really going to help us in the long run because it only sees a few feet ahead of it. Or we can potentially, for a larger scale project, use a high purity germanium detector. We realize this requires a lot more cooling. However, if we have a pipe that is able to allow us, we could put some liquid nitrogen in the back and thus allow for the germanium detector and thus allow us to look for any isotopes that may be present. The mapping will be further improved. Right now, using only Arduino, it might not be 100% accurate, but we are determined to make this function a lot more readily available. And if we are going after any fissile material, we would want some boron to absorb a lot of the neutrons that is being output so we don't accidentally create a critical pile.
Our technology has a lot of applications in a variety of industries, particularly oil drill pipes, because the Earth's crust contains an abundance of radium, and many of those pipes are contaminated internally. However, our team foresees much larger applications, particularly in the project of maintaining and renovating waterway infrastructures. Each day, 14,000 people experience emergency water damages. By the end of this presentation, that will be approximately 98 people that are affected. This might not seem like a big problem. However, insurance companies reported a total of $2.5 billion every year for water damages and molding. In addition, the American Water Works Association conducted a study that concluded that if we are to continue our current water service and increase and expand our system to supply the needs of a growing population, we will have to spend over $1 trillion within the next 10 years. Our technology, if implemented, would allow operators to oversee and assess the internal structural integrity of pipes to assess corrosion and other water damages.
So remember, use the ants, save the plants. Thank you. We are 4.0 cleaners, and thank you for listening. Do you have any questions?
Thank you very much, Ant, 4.0 cleaner. All right, judges, you have 5 minutes for questions. Anybody?
Yes, what level of radiation will your ant withstand?
Well, sorry. Okay. So during our research, we found that most contaminants aren't actually very high radiation and thus won't really affect the camera or electrical works. However, this device is very cheap, and if it were to experience very high levels of radiation, it is very easy to dispose of.
Can you speak a little bit more about the cleanup portion of it? You said that there's a vacuum on there. How do you know which side of the pipe the contamination is located, and what kind of maneuvers do you do with the robot to remove the contamination?
Of course. So our vacuum is at the very bottom of our robot, and thus so is our Geiger counter. So being able to spin in a 360 degrees, which is something we plan to, and we are in the process of implementing, we can determine just where the spike of counts per minute is, and thus we can determine where the contaminant is. We can also, we are not actually cleaners. We are going to be able to take a sample of whatever contaminant it is, and then bring it back for further analysis.
Presentation was great. Appreciate you guys
Thank you.
putting all the work into this.
Thank you for being here.
I also noticed I didn't see any numbers in terms of projected forecasts on costs, maintenance for this solution. Was there any
we
consideration
didn't think
there?
it was very good for the business people to put a bunch of numbers up there, but we did do those calculations, and it's not actually very expensive. We're looking at maybe $100, $200, and that's currently, and we have not thought of more possibilities.
And then I guess follow up to that is relative to other solutions that are out there on the market today, better, worse?
Well, to add on to that, or to answer both questions, we tried assembling our own model based on things we could find in the market, particularly Amazon, and we found that we can, without a doubt, fit everything within its dimensions, its required dimensions. Additionally, something that sets our system apart is we have spring systems, as he was explaining with the tracks, that can both contract and expand depending on the pipe that you are inside. So it is applicable to a variety of sizes. It is not designed for just one. And that would allow for reusing in the future.
Thank you.
Talk to me a little bit more about the connectivity piece of it. You mentioned autonomous, that it can run on its own. I mean, I can envision a scenario where most of the piping is not going to have a Wi-Fi signal around it. So how is that going to come back together, and what's the software requirements for pulling the data, I guess, out of it?
Looking at the requirements, our biggest concern was the safety of the operator. So we designed it so that it would be a minimum of 50 meters from the operator, so it could move by itself, I guess. The autonomous aspect is we would use the sensors to allow the system to operate itself. Many of the components we looked at have their own Wi-Fi signal. The reason we chose Wi-Fi is because it has a larger range compared to Bluetooth, and it is also more reliable. So the pipes themselves won't have Wi-Fi. It will be the components of the system itself.
It's also possible to connect up a router to it. So if you need to extend the signal at all, a lot of times you'll be using this within a plant. So there's possibly electricity near you, and thus you can possibly connect the router and thus send signal back to the operator. Thank you.
You said 7 hour. You said you had a 37-hour battery life. There was a lot of empty space in the internally to your design. Have you considered putting more sensors or anything else inside that would lower that battery life but give you more functionality in your design?
And I want to commend this team for not falling apart during the tremendous audio teams. It takes a tremendous amount of composure to not fall apart. And y'all did a really great job because we've been having this audio problem. So we apologize for that, and we're going to fix that right now. A quick break. Don, do you hear that now? Okay. You should be solid. Okay, good. All right. Give me a second here. No, y'all don't have to deal with the microphones anymore. I believe, judges, I believe this is going to work. Yes, this should work. And I believe that one should work. That one not working, it may not be on. No. Yep.
Test. Yep.
Okay, judges, y'all's mic should work. This is now wired. I'm very frustrated. Okay, we spent a half hour trying to make all this stuff work, so I apologize for this for everybody. However, and that first team, again, I'm going to tell you, that is hard to do. You guys did a great job holding your composure in the face of all of the technical difficulties that we had. So where are y'all? Y'all did a great job. I mean, really, congratulations. I mean, that was hard to do for professionals. And y'all have not done this necessarily, so I really want to commend you. That was outstanding that you just kept forward in the face of those difficulties. Sometimes you're going to do that. I've had fire alarms go off. I've had, all kinds of stuff happen. So that y'all kept your composure and kept going with that was really cool. So I really appreciate that. So congratulations on that. All right. And we're going to, Don, tell me when. All right, welcome back. We've got our technical difficulties taken care of, and now we should be able to perform and go smoothly. I'm going to invite the next team up, and it's Rocky. So take it away, Rocky.
Thank you very much, sir.
Here is the clicker.
Oh, there's just a big arrow on it. It's very convenient. All right. Howdy, everybody. My name is David Gregorio. I am a super senior electrical engineering major.
Oh, I'm Brady Drew, and I'm a freshman computer science major.
I am Carter Radica. I'm a freshman, and I'm a computer engineering major.
I am Benjamin Fenaway. I am a sophomore mechanical engineering major.
I am Leonardo Escamilla, and I am a sophomore mechanical engineering major.
My name is Amir. I'm a second year PhD student in aerospace engineering.
And this is Rocky.
Humanity may be in trouble. The threat of thermonuclear war looms over us like Damocles' sword. Nations around the world are reaching their era of nuclear weaponry. Over 2,000 nuclear weapon tests have been performed since the bombings of Hiroshima and Nagasaki. The United States of America has begun to act as the unofficial police response of the world. But what response can there be to nuclear bombs? We are Team Rock E, and we believe that knowledge is half the battle. In order to be prepared for nuclear threats, you need to know where they are coming from. To accomplish this, you need a device that detects nuclear materials before they become dangerous.
Presenting the Rock E, a compact device that comes in all shapes and sizes. Capable of lasting for a full year in the field, the Rock E can be deployed in 1 to 5 drone teams. Rock E drones can be adapted for any environment, any chemical, biological, or nuclear agent, and any delivery method. The Rock E can also be configured as a safety device, detecting chemical or radiation levels and reporting them in real time. Combined with an alarm, Rock E would provide workers in high-risk areas with crucial information before disaster strikes. Our design is modular, easily concealed, and versatile. State-of-the-art components ensure accurate information, while energy considerations offer up to a year of operation. The lightweight design allows a single drone to carry a full team of 5 modules in whatever way best suits the terrain. The future of threat detection is here.
Okay, we were to invent a device able to detect materials used in weapons of mass destruction, specifically nuclear weapons. And the idea is to use this information to help prevent conflicts between weaponized countries. And this device is stealthy and can be delivered using a drone to suspected areas. It can also be put near the roads in order to detect transportation of such material.
In order to create a successful device, we had to face several tasks. It has to weigh 1.5 kilograms or less. It has to last about 60 days. It needs to detect nuclear radiation. It needs to monitor the movement of nuclear materials in and out of nuclear development sites. It has to report encrypted results to a satellite. And the most important of it all, it has to be hard to detect.
While we were brainstorming our designs, we came up with 3 alternate designs. The first design was a mobile unit that would patrol around the nuclear facility. The second design was a stationary design that would be implanted inside the facility and just scan around in a certain radius around the facility. The third design, the design we went with, was the mobile design that would drop in several drones to scan the area.
So the conceptual design we went with was a container that has sensors dedicated towards picking up radiation emitted by weapons of mass destruction, and it also can be changed in many different ways to be stealthy in a given environment. The example we have here is a rock. This can be suited into a rocky terrain, but it can also be suited in many different other environments.
So for the technical performance, Rocky had to be able to report the data to a satellite, and to do that we have a transmitter, low Earth orbit satellite transmitter, that could also report results to a satellite or a high-flying drone. And the Rocky also has to be able to detect gamma and X-ray radiation. To do that, we used a photodiode detector, and for neutron radiation, we had a detector that used semiconductor technology. And all of these technologies had very low power consumption, which is why we could be able to last 60 days, which was one of the requirements. And you can see a map, that is the coverage range for the satellite. So you can see that we have the infrastructure in place so that we can be able to report the data anywhere.
We've already done some of the math for you to save you that headache. By our calculations, our product will be able to last for a full year in the field, doing about 61-second scans a day, and those numbers are malleable. You can do longer scans, you can do less scans, more frequent scans. You can schedule those scans whatever time of day you think is the most pertinent. You can make it last a little bit shorter in the field and do more scans per day. All of these are mission-specific parameters that you can control. On top of that, because of the lightweight design, we are able to fit 5 modules in 1 drone, which means you can set up a whole team, you can monitor a wider area, you can have redundancies just in case anything goes wrong, and we've encased it in a thermoelectric shell that generates about 11 watts per day. This just helps offset the cost of scanning and power. This helps keep it out in the field for a little bit longer, and it helps with our heat dissipation. The innovative processes of this that we are the most proud of is that thermoelectric shell, like I said. On top of that, because it's such a small, compact design, it can be recamouflaged into anything for any specific environment. If you need it in snow, if you need it in rocks, if you need it in a tree stump, in a forest, any of these things are options available to you. We also believe that this could be applicable in several other industries, such as food testing or chemical plants, as you could use it to detect and report on chemical levels in rooms or radiation levels. Because of the modular design, you can replace any of the sensors and be good to go. Ladies and gentlemen, we are Team Rocky. Do you have any questions?
Thank you very much. Hey, judges, you have 5 minutes for questions. Please use your mics. They should be working now. Turn it off.
Yes, it does. It has a miniature GPS module in here.
It does not rely on GPS for the detection. However, having the GPS allows you to keep track of your drones and know if they've been picked up or if anything's happened to them.
Do you have a specific drone that you identified as the carrier that you want to type of
our need statement said that we had a drone that would deliver it and would transport up to 1.5 kilograms. But you can use just about any drone you want if you want to roll it in, fly it in, burrow it in, however works.
How long do you anticipate the battery life lasting for continuous scanning?
If you take it up to continuous scanning, we calculated that if you did about one scan every 3 seconds, you could have the battery life last for the requisite 60 days.
And does your thermoelectric solution depend on outside temperature?
Yes, that is based on ambient heat, but without that, it still lasts for a decently long time. It's only a couple days difference over continuous scanning.
Any other questions?
Because this appeared to be a very military application, we went ahead and ran the assumptions without worrying about cost as much. We believe that each module would run about $1,000 to $3,000. But if you were applying it in a different industry, you could switch out the parts. You wouldn't need a low Earth orbit satellite transmitter if you're just trying to relay it across the room.
So in the application that you guys are working within, who would be the end consumer? Who owns this product that you're created? And how would they go to market, so to speak, if we're targeting finding potential weapons of mass destruction in territory, say, how does that work? You guys in that consideration?
Anyone want to speak to that?
Towards marketing this towards other governments, I mean, we can present it in the same way that we've presented it now, showcasing the very modular aspects of how well it can blend into different terrains. We can also showcase the ways in which it can detect weapons of mass destruction, such as the different sensors. We have a sensor for neutron radiation. We also have a sensor for gamma and X-ray radiation too, which are commonly found in weapons of mass destruction.
As for the end consumer, like I said, we believe it was kind of a military need statement. Anything else would be kind of by client demand.
Okay, any other questions? All right, thank you very much. All right, for the third. Get ready to be able to provide your presentation. Come on up. Do y'all need a table? Looks like y'all need a table. Do you? Okay.
Y'all will be fine. We're almost there.
Howdy. I'm Matthew Novoa, junior chemical engineer.
I'm Shamari Reed, a senior nuclear engineer.
My name's Ian Tremblay. I'm a senior mechanical engineering student.
I'm Jason Tabulan, senior nuclear engineering.
My name is Jeremy Ringwood. I'm 10 days into the general engineering program here. We are a new exchanger.
The average American uses over 12,500 kilowatt hours of electricity per year. This energy powers our everyday needs, like cooling our homes, cooking our food, and keeping us informed and connected. In other words, our world could not function as it does without access to reliable power.
It is the strongest hurricane in modern records for the area.
In the wake of natural disaster, entire communities can be left in the dark. People lose contact with their loved ones. Hospitals are left without power. Life as we know it comes to a halt. What if we told you this could be fixed? That's where New Exchanger comes in. We provide power solutions for remote and devastated areas using advanced heat exchanger technology. This allows for us to safely and efficiently transform heat from a portable nuclear reactor into reliable energy, bringing the power to you.
Heat exchangers for a 10 megawatt nuclear microreactor.
Now, we do this for a multitude of reasons. Primarily is to save lives. It is shocking the fact that 1 in 20 hospitals are not prepared for even just the slightest power outage. As soon as they lose power, their necessary equipment, life support, respiratory, they're not prepared for the outages. These generators have the potential to provide backup power for these hospitals. Additionally, in the wake of natural disasters, there are corporations, global corporations, FEMA, Red Cross. We can ship these generators to them, and they can keep the local communities running even if a hurricane or tornado has just blown through. Lastly, military and remote locations. We can ship them. Most of them rely on diesel generators right now. First of all, it's very expensive to be shipping them diesel fuel to run the generators. Second of all, those generators require maintenance in excessive amounts. These nuclear reactors that we have, they provide very reliable energy for these remote locations.
All right, so our heat exchangers are capable of removing 10 megawatts of power from a nuclear core, operating at about 1300 degrees Celsius. They're easily transportable, whether that be by semi-truck, plane, or even barge. They are self-operating, so that means they can operate even without the presence of an operator. They have a 2% increased performance in regards to efficiency compared to traditional nuclear reactors. And most importantly, we have a built-in fail-safe integrated into our cooling system.
So some of the alternative solutions that we thought of a heat pipe helical solid thin tube. The reason why we chose this one is because we want to have the highest thermal conductivity in order to dissipate that energy into electrical energy. So some of the three different combinations that we thought of, working fluids in the shell was silver, lithium, and sodium. Now, as you can see at the top right, the thermal conductivity of silver is the highest. The reason why we didn't choose silver is because it's also the most expensive. So we chose sodium because it's the most abundant, and then it's also its vaporization temperature is much lower, so we can operate at lower temperatures.
So the solution that we chose to go with is actually a tandem cooling system. If you take a look at our prototype right here, you can see the red and blue clay on the outside represents hot and cold water flows. This is actually a pressure vessel surrounding the reactor core in the middle. And this will be a pressurized water cooling system. And then here in the top, we additionally have liquid sodium heat pipes, which are pulling heat out of the reactor core to generate electricity. And we have enough capacity in those to pull about 25% of the reactor's capacity of heat out at any given time. So this is enough to pull out all of the decay heat when the reactor is not operating, which provides a very important safety feature. And then some of the things that makes this a little different from reactors that are in existence today is primarily that tandem cooling system. Heat pipes have been used in the past, but it's typically on much smaller reactors, things that are designed to power space travel and things of that nature. They're only on the kilowatt level rather than the megawatt level. But with our reactor, we're able to remove 10 megawatts of heat due to our combination of those heat pipes along with the pressurized water cooling system.
All right, so in conclusion, not only do I invite y'all to be part of this fantastic business opportunity with New Exchanger, but I also invite y'all to be part of helping improve the quality of life globally. Thank you.
You guys have any questions for us?
All right, Judge, you have 5 minutes per question.
Can you say a little bit more about how your design is fail-safe? You made that claim, but you didn't really talk much about that.
So the main reason for this is not fail-safe, but it does provide a second alternative for cooling the reactor. Is, as I was talking about the heat pipes, they are able to take away the energy as the decay energy from the uranium in the core. And in some nuclear meltdowns which have happened, it actually starts from this decay energy, and they require no operator input. They operate completely autonomously. It's based only off of thermodynamic principles. It's a completely closed system. It's actually not even a loop. The heat pipe it's simply a pipe with ridges on the inside, and it carries heat. It carries heat away from the reactor core. So there's no way for a human to mess that up.
So you're saying that if you lost all power and water for the primary cooling system, the heat pipes would carry away, it would prevent a complete meltdown?
Yes, sir.
Okay.
Good job, guys. Nice presentation. Talk a little bit about the water requirements. If you think about a natural disaster scenario, most of the nuclear plants I've been at have, a large reservoir or on a river or something along those lines. How do you foresee that, overcoming the challenge of having access to water, good water, et cetera, in that application?
So requirement for our design is actually for the modular system to be located near a body of water. We did have a diagram showing that, and
sorry, I missed that.
Yeah, no, that's all right. But what happens is that whenever we're trying to cool off the water to bring back into the generator, we run through a heat exchanger using water from the local water reservoir to cool off the water to cool off the core.
Any considerations from a security standpoint, physical security? So if you guys deploy, a number of these units to places that are already a bit chaotic during a natural disaster, how are you guys maintaining or tracking, where these mobile nuclear reactors are located and who's kind of the watchman for them?
Well, to answer that question, the new exchangers we're only designing the heat exchanger. We're not exactly designing the micro reactor. And so our project was to design just the heat exchanger. And so we don't really know that question, so we can't really answer that.
So how heavy is it? How much does it weigh? You may have said that. I'm sorry if I missed it. How much do you anticipate it weighing?
Is this the reactor or?
Just your part, what you've done. I mean, it's okay if you don't know. I'm just curious because in a mobile unit that can be important.
We don't have exact weights at this point.
Okay.
However, a sodium system is fairly lightweight as compared to, other possible cooling systems. Sodium is not a dense metal, and also it has a much higher capacity to remove heat even than water.
And once again, because we are only designing the heat exchanger, a lot of that would depend on whoever buys our heat exchanger, what they would like to do with our product, and how. So depending on what they add to it is how much the final weight of the modular system would end up being.
What manufacturing method would be used to create these helical coils?
We were actually considering additive manufacturing methods. For example, like, sorry, the term is escaping, but essentially a metal 3D printing, which has been developing rapidly in recent years. You can produce much more complex geometries with that. And that's actually how we produced our prototype as well. Obviously not with metal, but with the fused deposition modeling.
Did you see if that's been done for these specific materials that you guys are proposing?
I know that it has been done with most super alloys. I haven't looked into molybdenum, but with Inconel, Hastelloy, those types of alloys, which are able to withstand the temperatures that we're working at, I know for sure that it has been done.
And thank you very much for your questions. All right, and the next team up. And, hang on. All right, and 101 dots.
Howdy, we're 101 dots, and our problem was the autonomous speckle pattern placement. My name is Kim Blankenhorn, and I'm an industrial and systems engineering junior.
Howdy, my name is Connor Jackson, and I'm a sophomore aerospace engineering major.
Howdy, I'm Brittany Jenkins. I'm a computer engineering major in the class of 2023. Howdy, I'm Laura Tolan, and I'm a junior management information systems major.
My name is Ian Tia. I am biomedical engineering junior. And we have prepared a video for you.
What would you do if you could prevent a disaster?
Would you tell somebody? Take steps to prevent it? How would you prove it?
Designed the pedestrian bridge that collapsed at Florida International
find
University.
out what occurred.
The death
what
toll
caused
rose to
this
6 today.
What
and
would you
that's a
do
desperate-
if you could go back in time? Taking inspiration from these image transfer techniques, we have found a solution to the problem. Digital image correlation measures change on objects under stress. The current application is time-consuming and inexact. So building upon digital image correlation, 101 dots is solving the problem of measuring deformation on load-bearing objects and buildings.
We live on faith that the concrete beneath our feet will hold us up, and we live on the faith that the steel around our bodies will protect us when we're flying down the highway at 60 miles an hour. However, time is not our friend in this faith, because if we do not maintain the steel around us or the concrete that we stand on, then the concrete will crack and the steel will warp until something undergoes catastrophic failure and needs to be repaired. To avoid these breakages, there is a method called digital image correlation that uses the application of an irregular speckle pattern upon a surface and measuring it with a high-fidelity camera to see what warpages occur in the material as stress is applied. However, an issue arises with the actual application process in that it is currently done manually, either with a Sharpie or a Q-tip. So we are now going to propose a method of doing it faster.
So from what Ian was saying about the problem, we decided to come up with a few engineering requirements to select our solution. So the first requirement is minimum degradation of the surface of the object that we would be testing, so that the process of placing the dots doesn't damage the object, but the tensile testing or the testing on the object is what would do it. Then the accuracy of the dot location, so making sure that the dots would be on the location specified by the optimal pattern given. And then repeatability, so that given different objects of the same kind, they would be in the same spot every time, consistently. And then also minimize setup time. A big problem with this situation is that there is a lot of tediousness for the person doing the setup initially on the dots, and then lowering the cost and producing a non-uniform pattern on the object.
So I just want to walk you through kind of what process we went through to arrive at where we are now. So when we were approaching the problem and looking at the considerations that Kim just talked about, we were really mindful of all of the requirements in selecting a solution. So 3 of the options that we came up with at the time were some sort of 3-dimensional inkjet printer that could put the dots on the surface of the object, some sort of radiation technique that would actually speckle the object using radiation. However, that proved to be not technically feasible, and then also some sort of handheld printer. So originally, we selected the 3-dimensional inkjet printer. However, about 24 hours into this process, we realized that that just didn't have the kind of scalability that we were looking for, and it wasn't something that we were really passionate about and excited about. So we kind of went back to the drawing board, and we arrived at our current solution, which we are very happy with, and which we feel has a lot more different applications in a variety of industries. And I will hand it over to Connor to talk about some of those.
Thank you. So our current product inside of 101 dots is called dot paper. It consists of 4 primary layers. The initial layer, as shown on the slides, is a gray cardstock to support the chemical compounds resting on top and to provide stability. The next layer up is a silicone-based transfer to then transfer the next layers above it. The next layer that's going to be transferred is a soluble solution that will then dissipate with water. And on top of that, printed on the coat is the dots itself, which are provided to us with the perfect pattern that we are trying to replicate on the object. The application that is used to apply it is we are receiving a speckle pattern. It is a random generated pattern. The pattern is then printed on our dot paper using any form of inkjet printer that we are going to keep testing and modifying. After the print has been completed, you then place it onto the object, and then you apply a water solution, and then after 3 to 5 minutes, the solution has then transferred and the layers have then melted away, and then you will peel back the cardstock, and then when you peel back the cardstock, you're left with a speckle pattern that is now similar to what they use with the Q-tips, and it is very accurate to what the engineers have given us, and it's very replicable.
So with our project, we wanted to demonstrate an accuracy, and so we wanted to use folding techniques kind of similar to origami to line up our objects with our paper to get it repeatable, and so we could do numerous tests over and over again and have reduced error in that. With this, we've used our paper and we can make it as big as you want, and we can take it from lab testing into full-scale applications and doing tests over time. And then we also looked into where else could this be used. Our paper could be an alternative for decals as more durable decals that can last longer, and ones that don't rely on not having bubbles in it and having less deformation.
And then we would like to introduce you to our prototype, which Connor is holding right now. So unfortunately, we were unable to get our hands on some of the materials we would like to use, which include a metal oxide activated pigment. We had printer ink, so it does not have the same level of durability that our actual product would have. But as you can see, this was done in minutes, whereas when I personally was designing the pattern that went on this, it took me a good 10 to 20. So I think this process really shows the quickness and the easy application. We also heard from someone who worked in the aerospace labs here that one of the issues they experienced was it being very difficult to get the correct kind of speckle pattern by hand. They would often have to repeat their tests, which takes valuable time. So we feel like this is a really viable solution to this problem, and we're really excited about it.
We'd like to turn it over to questions, and we thank you so much for this opportunity and your time.
Thank you very much. 101 dots. Judges, any questions?
Handle arbitrary shapes. If I can speak to that, the way we can handle arbitrary shapes is by receiving different already provided files that we've received from engineers. So, for example, if you're to do something spherical, the way that a globe is printed is in like pie shapes. So it's already ready to be wrapped around. So it is modular for more complex shapes to certain degrees.
I kind of an extension of that. So I guess in the process that you guys have, your speckle design is based on the shape that is going to be applied towards. It varies based on what the application is.
If I can speak to that, yes. So we were told in the problem, and this does correlate with what's going on in industry right now, so we do feel comfortable with this assumption. We were told that we would receive an optimized speckle pattern for the geometry of the object, as well as the geometry of the object. So that's how we anticipate being able to print the kind of paper that would work with an object and also have something that's already optimized for the geometry.
Okay. And then one follow-up on that then as well. For in terms of recording the deformation and the speckle pattern, I guess what is I guess how do you guys record that? How is it measured?
That digital image correlation, actually,
Can you ask the question again? I'm sorry.
Yeah, so you guys have the paper that you guys are applying the
Yes,
speckle
sir.
towards. So how are you going to be able to test where there's a, what's the threshold that this item that you guys have printed the paper onto is under too much stress and is about to break?
So we are currently designing the paper that the ink will then come onto the object. That's actually a question for what digital imaging correlation is,
Yep.
if I understand correctly.
Yep.
Digital imaging correlation is more about seeing the distance between dots moving as you bend, stretch, and twist pipes. So if you have a stationary camera and you are looking at these dots and you bend this pipe, you'll see some of them move away, and then you can actually see the change and then the stress applied to the pipe.
Okay, so your solution isn't to look at the
No, sir.
imaging piece of
Our
it. It's
solution
purely
is to apply these dots accurately
Got
based
it.
on paper we've already received.
Got it.
They're designs we have already received.
How forgiving is it going to be in the application if the operator installs it incorrectly on the first time?
It depends on how incorrectly the installation is. So if the installation does not receive enough of the water solution, then the ink won't come off or won't transfer. So the ink does not transfer, then you waste $5 worth of our dot paper, and it's just another cheap setup time, and it's ready to go again.
And it's something that can be adjusted for with training.
Yeah, to build off what Connor and Kim said, we feel like still the level of operator error is likely to be much lower compared to the usually hand-done method, which we have now. We also managed to find a research paper that someone wrote about using a similar type of transfer paper for speckle patterns. We also no one had ever done anything with it commercially, but that one research paper did show that there were some promising findings in a low error rate and that they were able to get within the desired accuracy using that method. So we do feel like it's a promising solution to the problem.
Okay, thank you very much. 101 dots. And the next team is going to be Hex Force. We'll be back in just a second. Okay, Hex Force, take it away.
Howdy. My name is Victor Vogt, and I'm a sophomore material science and engineering major.
Hi, my name is Emily Payne. I'm a sophomore mechanical engineer.
My name is Raul Benitez, and I'm a sophomore civil engineer.
I'm Diego Martinez, and I'm a sophomore mechanical engineering major.
Hi, I'm Jayesh Tripathi, and I'm a computer science engineering junior.
My name is Jessica Chapa, and I'm a sophomore biomedical engineer. We are Team Hex Force, and we're presenting Maroon Box.
The common factor among these disasters is that structural health was not adequately monitored to prevent failure. This has been happening for centuries. Proper maintenance and testing could have prevented many casualties.
Team Hexforce has developed the Maroon Box, a universal testing device that can measure vital metrics in locations and conditions inaccessible until now. Using optical fibers, it shines a new light on recording strain, temperature, and acceleration by providing thousands of data points where conventional methods failed.
This technique can be applied to solve challenges in every engineering field, from biomedical to nuclear engineering. From efficient prosthetics to automotive collisions, its portability introduces applications where its durability stands out from traditional sensors.
To design a universal device that could collect physical testing data in a variety of conditions.
The existing techniques right now are the event data recorder and the flight data recorder known as a black box. Now these two data recorders, they're used only on automotive industry or aircraft industry. The purpose of these data recorders is to survive crashes or unexpected events that would destroy or ruin the structure significantly.
So the problem with these existing data recorders is that there's no universal system to them, meaning that depending on your structure, you would have to connect cables in where you want the device to record the data. There is another problem that most data recorders do not have an internal battery, with the exception of a few airplane data recorders. So that you would always have to connect to an external battery source to power this device. They're not reusable. After the first crash, the data is to be saved, and you're supposed to find the data wherever it may be. Most data recorders are very bulky, and thus they're hard to maneuver if you take them in and out of spaces.
So in order to solve this problem, we created a device that will be able to withstand temperatures from 75 degrees Celsius on the low zero, 75 degrees Celsius, be able to record 30 minutes of data recording, weight less than 1.5 kilograms, be able to withstand 500 Gs of acceleration, and be able to take 3D measurements.
So for the design procedure, we first thought of a 3D cube that would be made of graphene. And graphene is a very durable, very lightweight material, but the problem that we experience with graphene is that it's very expensive.
This design would also contain the sensors inside the box, but we realized that it would make the measurements inaccurate.
We also considered a swarm design which would have a central data hub with several arms protruding from it, but we deemed this to be too complicated for our purposes.
Finally, we decided to go with the design where it would be a small box that could be stuck on a wall of the object, and that would take in the data.
And the advantage of this design in particular is that it's very compact and easy for the operator to install and use.
The outer casing of this box is made from grade 23 titanium alloy for its lightweight and high tensile strength. It can adhere to virtually any surface using a flexible epoxy resin, which also insulates the sensors on the outside from extreme conditions. These sensors on the outside consist of two fiber optic sensors, which measure strain and acceleration data, and then a separate Type T thermocouple, which measures temperature data.
And if we look at the inside of this box, so the design is going to be insulated from temperatures by an aerogel-based thermal wrap. It's going to contain a programmable microprocessor, which is going to transmit the data to our 64 gigabyte micro SD storage. It's going to be powered by a rechargeable alkaline battery, which is going to be charged through a USB-C port.
To use the Maroon Box, all you gotta do is apply the epoxy resin on the side where the optical fibers are and stick it to the wall of the object. The fibers are embedded in the epoxy resin in a way that it is also in contact with the wall so that it can measure the data.
And so once this data is recorded, it's going to be stored in the micro SD card, and that data can then be retrieved through the USB-C port once testing is complete.
So when we were first going through the designs of this, the dimensions, we originally imagined a typical structure, like I said, but we also explored maybe spherical items such as cans or other types of cylindrical vessels. But but they were just deemed unworthy for the internal components that we were using. So we ended up with a rectangular prism structure.
So one of our photographs was a cube 5 by 5 by 5, 1 inch thick on the inside. But since most of our components will be circuits, it was inefficient due to their size and their length. So our final rectangular prism ended up being 7 by 5 by 4 with a thickness of 1. This is a scale model, so the actual device will be smaller, it will be in centimeters. And then we estimated the final weight. The structure itself will be less than a kilogram. So the final component below of its many components will be less than 1.3 kilograms.
So what we are seeing is how the optical fiber sensors would work. Basically, optical fiber sensors have a grating inside them which would reflect back a certain wavelength of light, but when the surrounding changes, the reflected wavelength changes, and through that we can measure the change in the physical aspect.
So this box can withstand extreme conditions, and in that respect acts as a black box and safeguard any type of data you need, but it can also act under normal circumstances, not extreme conditions. It can act as a centralized hub for long fiber optic wires running alongside any surface, such as a building, in this case an airplane wing, which was used by NASA in that video, and that gives you an accurate strain temperature or acceleration measure at every single point along the wire. And this is extremely, this is better than conventional strain gauges because those gave one single reading at one specific point, and these can give almost infinite readings along the whole surface of the wire.
As for the innovative part of our design, it's affordable because compared to the existing techniques, which cost thousands of dollars just to retrieve the data, the maroon box only costs under $300. It's lightweight because it weighs as much as our cell phones that we carry every day. It's user-friendly because there's no need for any wires to install it. All you've got to do is to stick it on. And it's versatile because it can be used for many different aspects in engineering. When we first started this project, we couldn't even imagine how many different aspects it could reach out and solve. We are Team Hexperts, and we thank you so much for this opportunity and for listening about Maroon Box.
Thank you. Judges, you have 5 minutes for questions.
I'll try to get close over here. Talk about the data collection. You mentioned that you need to actually physically go to the box to get the data off, or is there another method contemplated?
So we initially wanted to transmit the data, but because we are using a titanium alloy, it is pretty difficult to transmit any kind of data outside the steel casing, especially for a black box. So we have a USB port through which we can extract the data out of it. And I know that brings in the question that will it be as strong with that USB port or not? But we're going to cover it with the lid, which will make sure that the strength is not compromised.
So you showed some videos on fiber on arbitrary surfaces like wings. Can you do that as well as this, or are you limited to the geometry of the box?
So we had a slide actually that showed a technique called finite element methods. So this could act as a centralized hub for long strands of fiber optic wire running alongside any surface. And in that case, they can collect data on strain or temperature from any surface, not at specific points, but throughout the whole wire, giving an almost infinite view of the surface.
Personally, if I were to use this project as a consumer or as somebody trying to design something, I would imagine that you could use multiple of these if you wanted to. Not necessarily have to spend the time to actually put out all of the cables, even though they're very helpful. Our system will capture the same data you need if you you only have to use one, but you can use as many as you would like. And I think that's what makes this product.
And the reason that we specifically incorporated the fiber optics into the design of the box itself was because, again, we were looking to meet our requirements for protecting this in some extreme environments. And so we wanted to make sure we were going to be able to do that and save the data successfully.
So the system, under extreme conditions, has to be able to record data for 30 minutes. So under 500 G's of force and extreme temperatures, it needs to be able to record data. So we have on the top and on two more sides to record in 3 dimensions. We have optical fiber, but this is embedded inside the resin, which would strain with any surface because it's highly flexible, giving an accurate strain measurement. And the Type T thermocouple would actually go outside the resin to be in direct contact with the body through measuring, and all of these can withstand the extreme conditions required.
Have you considered the epoxy or resin damping the true accelerometer acceleration data that you're trying to capture?
So that's, I think, kind of what Diego was alluding to here was that we made sure when we chose the specific resin we were looking at that it was going to be as flexible as possible while still providing the insulation and adhesive properties we needed. And so we believe that this is the best way to adhere our product to a surface and have as little impact on the optical fiber straining as possible, because the optical fibers we know will thermally expand and stretch significantly less than the resin will. So the resin will not be a limiting factor in the strain measurements.
Also, we did our research on the modular elasticity and thermal coefficient of thermal expansion for the resin and the optical fiber, and found out that it was a perfect resin for the optical fiber.
Okay, judges, thank you very much. Appreciate it. We are going to take about a 10-minute break. If everybody could be back here at 4:30, we will continue with the next team. All right, welcome back from our break, and we're going to continue the Aggies Invent final presentations. Again, this is for nuclear security, and we're going to now hear from the glue guys. They're a sticky team.
Howdy.
Howdy.
My name is Ian. I'm a mechanical engineering major, sophomore.
Hi, I'm Carlos Lago, a material science and engineering student.
Howdy, I'm Trent Ducko, a nuclear engineering major.
I am Joe Martini. I'm a sophomore petroleum engineering student.
Hi, I'm Tanya Lee from computer engineering.
Hi, I'm Sam Roth, electrical engineering.
Our focus is in adhesives and in sensitive high explosives. And we are
the Glue Guys!
Woo!
Who doesn't like explosions? But sometimes explosions go wrong. Glue is what holds all the bombs together, and without it, you have nothing. We need a glue or adhesive that is reliable and can withstand extreme temperature and conditions. So our US troops don't end up looking like these guys.
The what?
Whenever we say bombs in the videos, we actually mean insensitive high explosives, or we go as IHEs. All right, we're in a sticky situation, so if glue holds bombs together, then when it heats up, it expands, but when it gets cold, it contracts. This can cause lots of issues within the process. As we're about to see here, something might go wrong with all the microfractures that happen. Boom! See how there's, it's not too organized. You can have a misfire, you can have microcracks which lead to those misfires, and as a result you can have less efficient explosions. But we did find a solution. We specifically made a glue that's able to mix with the materials and have the same properties as the explosive. That way, it works. Boom. It's a match made in heaven.
I will now show you a physical representation of this. These are sugar cubes, not explosives, that we have glued together. And so this, imagine for a moment that it is the missile that you see up on the screen, right? The yellow part is the explosive. And for manufacturing purposes, you have to glue several parts of the explosive together. Now, when the adhesive is not the proper one, does not have the right thermal properties, and creates macrofractures, you have a glue that doesn't quite explode or sometimes creates those cracks, and you have an unhomogeneous explosive. And for that reason, we have formulated an adhesive that works.
Needs mainly that the adhesive matches the thermal and mechanical properties of the IHE. And there's 3 specific properties that we looked at, shown on the board, as well as separate manufacturing properties that we have to take into consideration when making our product.
So what exactly is our product? It's a mixture of 2 industrial polymers and an industrial adhesive. And what makes our product so innovative is that it stops the microcracks that occur because the adhesive is actually thermally similar to the explosive. What this does is it allows the adhesive to expand and contract with the explosive, and that optimizes the blast. What you're about to see on the screen are the 3 solid representations of our main ingredients, and we mix them together to get the properties we need.
To build our design, we have evaluated multiple alternative designs, such as some structures like common strip and some existing adhesives like superglue and UV lights. However, they couldn't solve our problem because they are not satisfying all of our requirements. Therefore, we have come down our decision conclusion based on what is most important. The 2 most important values were its thermal similarity and manufacturing feasibility.
Not only did we solve the problem for the U.S. military, we also have this method that can be applied to many different industries, such as mining, deconstruction, housing, automobiles, and most importantly, medical.
Our product works, and it will save a lot of lives. Thank you. We are the Glue Guys! Any questions?
Thank you very much. And judges, you have 5 minutes for questions.
Yeah, you said that there's 3 ingredients to your composition. What are the role of each of those 3 ingredients?
So the role of the polycarbonate was to increase our elastic modulus from. So you can see that has the larger value in addition to the Dimex, the glue. So I'm sorry, I can't see the numbers. The polyethylene also increased our value. So each individual thing had to take a role in either averaging up. We used the rule of mixtures in our value to come up with our 2 values. So each ingredient either up or increased that value or lowered it. And the reason we stuck with the polymers was because they're easier to mix. Another thing we considered was mixing aluminum, actually using the values for that work, but that would have created more of like a sand-like adhesive where you weren't actually getting the properties of the aluminum in the adhesive.
So what was your mixing technique? I mean, did you just stir it together? I mean, how did you mix it?
So we didn't actually acquire the adhesives. Well, first of all, over the weekend, there were businesses are closed that would supply some of these large, these industrial adhesives and polymers. So, but our idea was to melt down the polymers and mix them with the adhesive, which was already in the liquid form. And then, therefore, we would take from that, we would let it set, and then test the yield strength from that, and then that's how we would continue our research in the future.
Do you see this mixture of glue, is it comparable to what's out there in terms of costs? Is it more expensive because of how effective it is as being a flexible glue, or is it?
We found one similar product, and they used silver. And so something that's very neat about our formula is that it's all polymers, and they're very common polymers that you can find. The most expensive will likely be the adhesive, the actual bonding, which is the Dimex OP58.
And then in terms of production of this adhesive, is it much more complex to produce than what's out there today?
We can make a strong assumption that it is comparable. However, we can also say that this will give us better performance.
How did you guys ensure that it meet the 30-year aging requirement?
The 30-year aging requirement is a strong challenge. We get closer to what might be out there. I think the most important thing, though, is that we are keeping the explosive material intact. That's not fracturing. And so you could have a maintenance team that can come in and reapply the adhesive necessary versus previous solutions. If the explosive is damaged,
it definitely will not reach the 30 years. But that is ongoing research for us to get to the 30 years.
Okay, thank you very much, Blue Guys. All right, we're back for our hot and ready.
Howdy.
Howdy.
My name's Abraham Miranda. I was part of the team that worked on heat management for re-entry vehicles. I'm a freshman general engineer, and I was task manager.
Howdy, I'm Sierra Garcia. I am a sophomore general engineering major, and I was the media coordinator and researcher.
Howdy, my name is Ashok. I was part of research. I'm a computer science major.
Howdy, my name is Joe Heimer. I'm a sophomore aerospace engineering student, and I did the CAD for this project.
Howdy, I'm Paulo Seche. I'm a junior chemical engineer and I worked on the science structure.
Howdy, my name is Fabrizio Estrada. I'm a junior mechanical engineering student and my focus was in the thermoelectrical generator.
The thermostat is climbing to the triple digits.
That's right, Cynthia. You know, doctors say dizziness, weakness, nausea, those are all symptoms of heat exhaustion.
Emergency responders received a near record number of heat-related illness calls Thursday, reporting its third heat-related death.
We all know Texas heat. Now, imagine something worse.
You may be wondering, how do we solve this? H&R presents you the RRV Mark I, which does just that.
Our system is also capable of providing human cargo as part of its payload. Our system promotes reusability, while others on the market can only be used once. Our cost efficiency is better than others on the market today because others are only capable of a one-time use. Our system also helps in protecting the electrical components, which aids in reusability.
All right, so today there is a glut of new space companies, each trying to carve out a niche in the small sat launch market. However, none of these companies provide services for returning a payload from Earth orbit back to the surface. Our team has developed a fully reusable system to protect a spacecraft and its payload during re-entry. This system is suitable for returning cargo from the space station or from other points in low Earth orbit.
Like all successful systems, our system has a set of requirements. It's supposed to have 0 external power sources. The external shape of the vehicle should remain constant. The internal payload volume is at least 0.5 meters cubed, and the payload capacity is at least 300 kilograms. The internal payload temperature should be kept below 300 Kelvin, which is approximately 80 degrees Fahrenheit.
What we have created is a reusable reentry vehicle that has a multi-layer installation system that would prevent direct heat from affecting our payload. And so when we were designing our systems, we considered many different nose tips or nose shapes, and so we considered a narrow point shape, a blunt shape, and a
Saucer shape.
a saucer shape, yes. And so we ended up picking a blunt shape because it would widen our bow shock. And so with that, we also have a reference scale for our vehicle. It would be a little bit, or it'd be smaller than the SpaceX Dragon. And so here's more on our design.
So basically the blunt, we have chosen the blunt body because it's similar to other flight approved test vehicles, and also the blunt body, it has a larger surface area, ergo giving the heat more to expand upon, and also the blunt body, it will follow, it's passively stable, and it will follow ballistic trajectory.
Now, our craft would be located at the nose of the aircraft, and it would be facing the flight direction path. Components such as aviation systems, batteries, or communications would be located at the very center of our craft, protected by the heat shield, along with the pressurized payload. Now, for our nose systems in our aircraft, we use density similar to previous shuttles and rockets in order to determine approximate total mass of the craft. We use a pressurized fed water system to cool our heat shield. And how we do this is that the water goes through a network of tubes in a heat shield, and it's similar to the tubing of liquid fuel rockets. And with this system, we can get rid of approximately 30% of the heat that goes into our aircraft, so that way it doesn't reach our payload, but it's essentially discarded through 2 valves at the rear end of our craft. Our heat shield is composed of a multi-layered system of different materials. The first material, the windside shell, is a carbon-carbon material, which is then followed by our water tubes, which take in most of the heat. Following that, there's a support titanium layer, which is pretty resistant against heat. It helps to the structural integrity of our craft. And finally, we have an aerogel coating, which is not only it doesn't only insulate, but it also helps as a mirror coating for thermal radiation that may pass through our carbon-carbon layers, our water tubes, and our titanium layer.
Now, for an extra challenge, we were tasked to find a way to generate electrical power from the heating that the spacecraft would endure. And so we thought of different ways that a thermoelectric generator could take advantage of that heat to our advantage. And so the way that the thermoelectric generators work is that there's a cool and a hot side. And so and with the temperature difference that occurs, it allows for a current to be generated and for electrons to flow. Now, a possible route that this could work is that it could be placed somewhere in the path of the working fluid, and it would absorb a lot of the heat from that fluid, and with that temperature difference, it would generate a current. And so, putting a lot of these generators together create a power to either store in a battery or to power some small electronic systems in there. Another method would be to simply think of a strategic way to put it in the spacecraft, which could has like a hot and a cold side to have a continuous rate of heat transfer. And we believe this to be the most viable solution because there's no moving parts, and it can also be scaled up as desired, like with all the generators that you could put in there. And so it eliminates the risk of having a complex mechanisms.
Okay, so the mission profile of this spacecraft is similar to other spacecraft that visit the International Space Station. It will be launched on a small or medium lift rocket, such as the Falcon 9. In the arrangement shown, you can fit approximately 6 craft per launch, and it could be taken up to a rendezvous with the International Space Station or other orbits, sun-synchronous, geosynchronous, other orbits that customers may require. It can remain on orbit for months at a time, performing experiments for that customer, and if it's sent to the ISS, you can transfer your payload into the station. You can have down mass of approximately 600 kilograms, as we said. And it's a very high turnover rate. The ISS will never be without supplies for more than a few days, and it can be recovered any point on sea or land by a helicopter, so it never touches the water, it never touches the ground, and it is rapidly reusable. That's the focus of this vehicle.
So future developments, since we are choosing a blunt body shape, the time during the re-entry phase will be a bit longer. However, we have the application of a air jet would be ideal, as it would push the Mach disk created by the bow shock away from the actual vehicle. So, yeah.
Thank you very much, and it's time for questions for the judges. Judges, you have 5 minutes for questions.
What happens if your water freezes in space?
It's kept thermally regulated by the same way the other electronics are. If we want, we can add active radiators that deploy from inside the hatch. So it's with the other temperature regulated parts of the spacecraft. And it's not in the tubes during the flight. It's in tanks.
You mentioned that it would be able to take passengers, part of the payload. How many people would you say?
Well, we've taken into account that our payload could reach up to 600 kilograms overall, and that's the maximum amount we estimate it for.
I think we were trying to say that this vehicle isn't human rated, but the same technology could be used to make crewed vehicles that have reusable heat shields.
Are there any safety issues from having hydrazine on board?
Hydrazine is chosen because it's almost all spacecraft use a monopropellant or bipropellant thrusters, hypergolic fuels in space, and we just went with a very typical run-of-the-mill fuel. We don't anticipate safety problems any more than other spacecraft anticipate problems from the same fuels. And it's regulated in temperature just like the rest of the spacecraft.
Why did you put the cooling channels between the carbon fiber and the structure?
So what we wanted to do here is, through using the water tubes, we can absorb most of the heat, and that way we can take the heated water, heater vapor, to the release valves, where they would be connected to the thermoelectric generators, mildly exposed to the thermoelectric generators. That way we can take some of the thermal heat in, turn it into electricity at the same time it's being propelled outside of the spacecraft.
So this is where the future development would come in. With that electricity generated from those thermoelectric generators, it would be used with this application, the forward-facing air jet.
We used boiling gas to force it out the front. That's what we considered, but decided that it wouldn't be included in this design.
Okay, thank you very much. Thank you very much. I'm ready. The next team is insects, so we're going to find out all about them. And insect, take it away.
Howdy. My name's Athena Sagadevan. I'm a PhD student in nuclear engineering.
Hello everybody, my name is Lee Baca. I am a junior in electrical engineering from West Texas A&M.
Hello everyone, my name is Koimo. I'm junior in nuclear department.
Howdy everyone, my name is Sebastian Trinos and I'm a sophomore in the mechanical engineering department.
Howdy, my name is Clara Stadler and I'm a computer science major.
We are insects. Does terrorism scare you? Does the idea of a rogue nation having weapons of mass destruction make you feel endangered? If so, don't worry, our insect can save us all.
From using those weapons without the proper intelligence. Insect is a small drone that can covertly enter an unknown facility and determine whether or not there are dangerous weapons of mass destruction inside.
Our insect is a two-part system. The first part are three little drones that are going to enter a facility. And the other part, enter a facility covertly. The other part is a larger drone that'll go in through an air vent. The insect is capable of various modular designs and can be used in multiple types of situations depending on what type of sensor is mounted on it. For our situation, we're simulating a weapon of mass destruction facility. So we have radiation sensors on these drones. The first step is for the drones to infiltrate the facility through numerous ways. An open door, a cracked window, an air vent, something like that. We assume our drones are in the system. Once the drones are in, they'll find a discrete place to land and start collecting radiation signals. These signals will then be used to determine whether or not a weapon of mass destruction is present. The radiation signals are also spectroscopic, so they can be used to determine what kind of weapon is being used in that system.
So in order to get around a facility such as this one, we need to be small enough to where we can't be easily detectable by people inside this facility, but still large enough to where we can carry the right equipment. So to approach this problem, we considered a helicopter or a quadcopter first and determined that they might be too large. If you see one flying around, it doesn't look like it's supposed to be there. So our design is much more compact, and in order to get in such a little compact package, this is to scale, we decided that we need to find something that's going to be sort of in the palm of your hand and pretty flat. This is enabled through the queen bee. So the worker bee communicates with the queen bee, and the queen bee holds some more robust equipment that would be needed to get the information that the worker bees get from within the facility.
Presently available drones with radiation detectors are bulky and can be seen from far. What we designed is at least 10 times smaller than commercially available products. Like I mentioned before, this doesn't only detect, but can identify the type of radiation using silicon photomultiplier detectors that are mounted onto this little bug. It is fast, modular, and compact.
We decided to base the design of our worker bee drone off the University of Pennsylvania's Piccolissimo drone. We chose this as the basis of our design because it is small and it's simple, consisting only of two parts, the rotor and the body. It has less parts that can be a possible site of failure, and less moving parts to make for a quieter drone. Despite only having two moving parts, it still maintains maneuverability in all directions. To assist our drone in navigating the facility, we've incorporated a linear scan infrared camera on the body of the drone. So as the body of the drone rotates, the camera gets a 360-degree view, which is incorporated into a single image, which increases the situational ability of the drone operator. Battery life is an important consideration when designing drones. After doing power requirement calculations and comparing current off-the-shelf components that meet our size requirements, we determined that our drone would have 15 hours of continuous sensor usage and 15 minutes of flight time. Compared to the University of Pennsylvania's Piccolissimo drone, this is a 1.5 times increase in flight time.
Another one of our requirements was that the small worker bee drones needed to be able to communicate their detection data wirelessly. The transmitters on these small drones for mass and lift purposes cannot be large enough to transmit that data outside of a secure facility. Therefore, we have the queen bee drone who sits in a nearby air vent or somewhere nearby where it won't be detected, but it carries much more powerful transmitters. Therefore, the worker bee drones transmit their data to the queen bee drone, and the queen bee drone transmits that encrypted data to an offsite controller. Our design utilizes multiple innovations that make it unique. In researching commercial cases for the detectors we were using, the gamma ray detectors, the cases that were used were too large and unnecessary for our design, so we designed a custom case to conserve space and weight while still maintaining functionality. Probably one of the most significant innovations of our design is its small size. The presently available drones that also do radiation detection are far too large to be covertly operated. Additionally, its triangulation features using a swarm method of multiple worker bee drones allows us to precisely locate the actual source of any detection of a leak or radiation or precursors of any kind, depending on the sensor. And additionally, it uses encrypted data to keep it safe.
Right, because this is a modular design, so there's so many things can be improved upon this. So first of all is the autonomous system. So the worker bee is gonna will be controlled autonomously to increase its efficiency and reduce human interaction from the design. The second of all is the the second of all is the camouflage technique can be better. Depends on the certain situation. Let's say in desert, in facilities, it can be like color based on the certain background. And the most important thing is that the worker bees can be wirelessly charged from the queen bee right here, so that you can expand the range of working. So, because the system is built upon really basic components, so it's very cheap to manufacture, and it's very cost effective. And we don't design the system based for the government only. We design for many areas, so the system can be switched to many sensors commercially available on the market to make it more unique for a certain situation. Let's say chemical plant, nuclear facility storage, nuclear waste, anything.
Our queen bee and worker bee drone system is better than any other drone system out on the market because it is smaller than anything else on the market, therefore stealthier. It is modular, so it can fit different mission profiles. And using the swarm method and triangulation, it can locate precisely where a WMD is, a chemical leak, or whatever it is that you decide to use our drones for. We thank you for our time, and we're open to any questions you may have.
Thank you very much, Insect. Judges, you have 5 minutes for questions.
Hi. So is the operator is outside of the facility, right? Where we are, and is the operator operating the queen bee or the worker bees?
As of right now, we imagine all the drones being manually operated. Making them all autonomous is really beyond the scope of what we were trying to do this weekend, but that's something we'd like to make happen in the future.
And are they maneuverable?
Yes. Even though
I mean, I don't know if you've ever tried to fly a drone, but it can be kind of hard.
Yes, the worker bee is surprisingly maneuverable, even though it has so few parts. If you look at the model that we have, you'll notice that the motor and a lot of the components are offset. So this offset center of gravity causes oscillations when it's operating. And by using controlled engine pulses, you can use these oscillations to maneuver in a horizontal plane.
Okay.
For the takeoff of the worker bees, the described purpose is to fly through air ducts. Are you sure you're going to have enough space to get stable flight in that type of area?
So we didn't design the worker bee to be flying within an air duct. It's more for it to be inside of like an open facility where there might be nooks and crannies to where it can hide and collect the radiation data. The only thing that would be inside of an air duct would be the queen bee. The idea of the queen bee is that it's somewhere where it won't be visible to humans, such as an air duct. That's why there was more of a sneak factor to a worker bee.
What material is the drone casing made out of, or envisioned to be made out of?
It's 3D printed plastic.
Plastic.
Yes.
How loud are the worker bees? Do you have any sense for that?
Well, because like I said, it has only two parts. It's quieter than other drones, its size. And in the future, given more time and more funding, we'd like to design a more efficient rotor system and use better components. So everything that we based our measurements off of was all off the shelf.
Package. If you got one-to-one to the.
I think the minimum you need for triangulation would be 3 worker bees and then 1 queen bee. But given the time to develop the software, we may be able to up that to many more.
Okay, thank you very much, Insect. Final presentation this afternoon is from Nuclear Warriors, and if they will come forward, we will get us online that all these projects started Friday afternoon. Students actually formed the teams and then put the entire need statement, designed, built their prototypes, and designed and built the presentations and the briefings here all since Friday afternoon. At 4 o'clock we started, and I reminded the teams at that point in time that they seemed like 3 o'clock on Sunday is going to be a long time from now, and that it was going to seem like, you know, you've got plenty of time to be able to do this. I also mentioned to them that I was going to be their worst enemy as I was going to keep them on track. And I then reminded them that in actuality, 3 o'clock on Sunday was about 4 hours from 4 o'clock on Friday afternoon. All right, none of you believed me at that point in time. Do you believe me now? Yeah, it seems like it was about 4 hours from now. So this has all been accomplished in a very short period of time. Congratulations to you. And I think the judges are just about ready. And Nuclear Warriors, please bring us home.
Howdy, my name is Tuwin. I'm a junior in petroleum engineering, and our team's name is Nuclear Warriors. This is our project for the Aggies 2019 Invent called ShieldX. And that's a picture of my team.
Lee, I'm a sophomore aerospace engineering student.
Howdy, I'm Jessica. I'm a junior mechanical engineering student.
Howdy, my name is Liam Fortier. I'm a sophomore nuclear engineering student.
Hi y'all, my name is Alofi. I'm getting a master's in nuclear engineering.
And that's me.
Howdy, I'm Antonio. I'm a freshman in general engineering.
Damage taken upon re-entry into Earth's atmosphere is a primary concern of anyone enterprising into space and beyond. In fact, 80% of all material launched into space never returns, a substantial portion of which having been lost to the extreme heat experienced by objects plunging through the atmosphere.
The uncontrollable debris created by atmospheric re-entry has a 1/992 chance to hit a person, on average, often to detrimental effect. In order to combat re-entry damage, we designed a system we call ShieldX.
ShieldX uses a reinforced carbon-carbon composite in order to create a heat-resistant conical structure supported by shock-absorbing components in order to absorb and redirect heat and shock waves around the embedded and protected vessel. ShieldX solves these problems by protecting the main vessel and by burning away into CO2 gas instead of damaging chunks.
To bring back to us a space payload undamaged in order to reduce the cost of launch and the loss of payload, and while remaining self-sustaining when we are in space. In order to meet that goal, we have to overcome the challenge of reduce the heat damage during atmospheric re-entry using additive manufacturing or 3D printing. And now my partner Antonio is going to talk more about existing technology.
So today, in order to get a spacecraft back from Earth, you have to start from the very beginning. You have to design a spacecraft with a heat shield. You have to design around the heat shield, which prevents you from adding extra instruments that could be put on the same spacecraft. Once you have that design, you have to manufacture it and you put it on a launch pad. However, if that heat shield was not there, you could have put more scientific instruments on it. And having the heat shield on there has added costs when launching. So you launch also, so when you launch the spacecraft, you launch it up, you have to carry all the dead weight from the heat shield all the way to your destination. And when you're coming back, you finally use that heat shield you carried all throughout your journey freeze it for 3 or 4 minutes while you re-enter the Earth's atmosphere, and then you let it go into the ocean, never to be seen from again or used again.
So in order to achieve our goals, we have to meet these requirements. It needs to withstand re-entry loads of up to 500 Gs, resist temperatures of up to 1600 Kelvin for 5 minutes, also support a 400 kilogram payload, and the density can't be more than 5 grams per centimeter cube.
So when we took a first look at this problem, we thought of conventional heat shields. First off, we looked at a spherical design, but when we ran simulations on it through thermal simulation and also a fluid simulation, we found that it is not aerodynamically efficient at hypersonic speeds above Mach 15. Then we thought of using a flat bottom heat shield. However, when we looked at the CAD, it told us that it took up too much extra material to make up the heat shield, so it wasn't cost efficient. Then someone had an interesting idea that to use the Venturi effect, to where air comes into the tube, and as it goes through the tube, it slows down enough for the payload to be protected from the hot gases, as the hot gases won't be as hot as if it was directly making contact with them. So for our final design, we came up with a conical shape. We put the payload on top, and we manufacture the cone to protect the payload as it comes into the Earth's atmosphere.
For our material, we chose reinforced carbon-carbon with titanium. The advantages to this include that it's lightweight, it's about 1/5 of steel, it has high resistance, high heat resistance, which is also part of our requirements, and it has no signal interference, which is very important when communicating with ground towers. Some of the disadvantages of just carbon-carbon was its low impact, which we solved by reinforcing it with titanium.
And here's a heat simulation of our final design. As shown in the picture, whenever the heat comes in, usually the base of the heat shield will experience the highest temperatures, and as seen in the picture, it's roughly around 1600 Kelvin, which also fulfills our second requirement of resisting temperatures of 1600 degrees Kelvin for up to 5 minutes. Also seen in this graph, from the last 300 seconds, the temperature rises all the way up to 1600, proving that it could resist the temperatures and fulfill our second requirement.
So our product is innovative because of the fact that it can be manufactured in space. And the way we do that is by using additive manufacturing, also known as 3D printing. And this allows us to basically design a different conical structure for any payload module. That way you can have an individualized cone so that it's the most efficient as possible. Additionally, it saves you time and money by being able to rebuild a conical structure on top of undamaged layers from one that's been used prior. You might be asking, how the heck are you going to build it in space? The great news is NASA already has a facility on the ISS that's capable of producing anything from small tools such as wrenches that they use every day on the space station, all the way to lunar bases, which they're planning to start producing in the coming years. And by using additive manufacturing, it saves y'all money because it saves you from human labor as well as resources, since you can continue to build on top of used layers already.
In addition to that, the markets we're looking at is the U.S. military. They use a lot of missiles, and in addition to that, submarine warfare. NASA is also a big player in this industry, as they already have their manufacturing facility up there, as well as other private companies such as Lockheed Martin and Raytheon.
And that concludes our presentation. Thank you for your attention. Any questions?
Judges, you have 5 minutes for questions.
presumably the heat shield will need to be larger than whatever's coming back into space, and most of these additive manufacturing techniques that you guys mentioned are being done inside the shuttle. I would assume that to create this heat shield that need to be done outside. Do you guys have given any thought to that?
Yes. So one of the ways that you can approach that is by building it in several segments and transporting them outside if you want to use that current technology. Otherwise, as more 3D printing systems get moved into space, obviously you have larger systems as you progressively work your way up. So that's another option. NASA has shown that they're willing to work with private companies such as Built in Space, which uses 3D printers in space to build objects and then sell them at a high profit margin here on Earth.
What technique are you using to 3D print the titanium reinforced carbon? And how do you make sure you get the right structural properties for that?
Okay, so there's a couple of techniques that you can use for titanium to have it shaved down before and then build it out of on a 3D printer. It's a little bit more of an advanced technique and it's new. So we'd have to incorporate some of that with that space age technology of 3D printing metals. But once we start incorporating that, then it would be as simple as printing it as a second layer onto it.
We definitely looked into those. We researched about that, but it's relatively new, so we can't really give too much information on that. But we know that it's being developed currently, and we further plan on using that technology as soon as that comes out.
And one idea we had as a standby technique was to use since carbon-carbon is basically a weave of two different types of carbon, instead of using only two types of carbon, we could also interweave Kevlar, which would give it that added impact strength. However, that has slightly less heat resistance than titanium. So we wanted to use titanium in an ideal world, but otherwise we can use Kevlar.
Are there any impacts to the systems leaving low Earth orbit without a heat shield going out to space? Because I think that was part of the solution design, was that there wasn't a heat shield leaving, right?
Part of the solution design was to protect against the heat. Yes, there are a lot of impacts because there's a lot of debris in space. So a lot of that causes impact. And we did look forward to that using such high, they have such high yield strengths. The materials we chose, reinforced carbon-carbon and titanium, those have high yield strengths that kind of prevent from all those space debris, but it wasn't part of the problem we were trying to solve, but we definitely did look into it.
Okay, thank you very much, Nuclear Warrior. All right, the judges and I have a very difficult task ahead of us. The judges are going to enter the rest of their scores. We're going to retire for about 5 minutes or so, maybe longer, depending on how difficult it is to actually choose the winner. And then we will be back in touch with each other, and we'll bring you back in here and we'll announce the winner. While we're doing this, while the judges and I go through the deliberation, I'm going to ask everybody to go out to the steps right out by the Starbucks. We're going to Howdy and welcome back. I'd like to welcome you back from after the judging has all been done for this Aggies Invent, really targeting nuclear security. The judges really had a very difficult time, and I know I say this many times, but in this case there was a very difficult time to actually try to rank you in terms of your presentations. The comments constantly were that they're still amazed at how much you've been able to accomplish. There's more to be done. Again, let me remind you that as part of engineering entrepreneurship, if you'd like to continue to pursue this, we have an opportunity for you. We have the opportunity to take you up and include you in our incubator program, and we'll help you continue on. You'll have access to more free resources to commercialize your idea than you ever will again in your career. And in fact, with some of the NSF programs that we have, we'll actually pay you to determine whether or not your idea is commercializable or not. So if you're interested in that, please get back in touch with us, and we'll be more than happy to plug you in. All right, without further ado, then what I'm going to do is I'm going to ask Dr. Diane Hurtado to come up here. And Dr. Hurtado is the Vice Chancellor who manages the relationship between Texas A&M University and Los Alamos Labs. And one of the things that we're trying to do is to get much closer and work together, and this is part of that overall program. So Dr. Hurtado was very happy that she's going to be here today. And she's going to be handing out the third place. I'll remind you, you can take pictures with this. It's not cashable, all right? So please leave my checks here. Take pictures, you know, do whatever you want to with them. Make sure that you post it, do whatever, but please leave my checks here. For those of you, we will be depositing this in scholarship money. You'll see this in your teams, and scholarship money in your student accounts. That's how you'll actually wind up seeing it, okay? All right, so for the third place team, it's the Nuclear Exchanger.
I think y'all need to stand behind me because I'm so short. So, all right, okay. Does that work for you?
I think we all should take the check too.
Okay, yeah, take the check, hold the check.
Getting close, 1 and 2.
Good?
All right, congratulations. For those of you who have prototypes, I request that you place the prototypes back on the back table back there. What we'll do is we'll bring those into our office, and that way whenever you want to know where they are, we have them. You won't be having to try to chase down a team. So if you'll, a team member, so if you'll take any of your prototypes, put it on the back table there, we'll bring it into our suite. We'll also show other people what you've been able to do and accomplish in this period of time. So we really appreciate that. I'm going to ask the gentleman from Accenture to come up here and provide the second place team. And the second place team is Hex Force.
I'm just impressed you guys have a suit. I didn't own a suit. Congrats. Yeah, no, good job. I think you did a good job. Thank you. Yeah, well done. Yeah, well done. Thank you. All right, also hold it. Go for it.
Yeah. Thank you very much. All right, and finally for the first place team. The first place team, before I get into that though, I want to remind you that school starts again tomorrow. Sorry about that. Y'all have all done a really fabulous job this weekend. Remember where the Engineering Design Center is. Remember where we are. We'll be doing Aggies Invent 3 times a semester. The next one is on energy. The next one is on the Special Operations Command. So we'll be working to develop and design something for our special forces. Then in January, we'll be doing with vet medicine. February will be Invent for the Planet, where we believe we'll have as many as 40 universities involved around the world. And then finally in April, we're going to be doing something with a company that some of you might have heard of, and that's Facebook. So it should be an interesting year. Again, for the first place team, I'm going to invite our 2 gentlemen up here from Los Alamos Labs. They're great sponsors and provided just tremendous mentors throughout. I also want to remind you that tomorrow, if you're interested in nuclear security, there's a Nuclear Security Day right here, so you can find out a lot more about career opportunities and an opportunity to be able to work more directly with our partners in Los Alamos Labs. There's some material in the back here as well if you'd like to pick it up. So please come to the event tomorrow sometime in these rooms and learn much more about Los Alamos Labs. Again, so for our first place team, it is Rocky.
Thank you so much. Congratulations. Thank you. Thank you so much. I'm sorry. Thank you. I'll take that. I'm sorry. I'm sorry.
This seems long. You can do it.
All right, congratulations. Congratulations. All right, thank you again. This concludes this Aggies Invent on Nuclear Security. I hope you've enjoyed yourselves. Please return any material that you checked out from the Engineering Design Center. And please lay your prototypes out there. We will keep track of them. Again, remember engineering entrepreneurship, and we look forward to seeing you around campus. Thank you very much.